Another day, another story. Black holes are one of the most fascinating and mysterious phenomena in the universe. They form when a massive amount of matter is compressed into an extremely small space, creating an object with a gravitational pull so strong that nothing, not even light, can escape from it. Here's a breakdown of how they work. Welcome to Tabo Eminent Channel. 1. Formation of black holes. Black holes can form in several ways, including stellar collapse. When a massive star exhausts its nuclear fuel, its core collapses under gravity, potentially forming a black hole. Merging objects, neutron stars or other compact objects colliding can form a black hole. Primordial origins. Some black holes may have formed during the Big Bang. 2. Anatomy of a black hole singularity. The core of a black hole, where matter is thought to be infinitely dense and the laws of physics as we know them break down. Event horizon, the point of no return, where the gravitational pull becomes so strong that escape is impossible. Once anything crosses this boundary, it's consumed by the black hole. Accretion disk. Surrounding the event horizon, gas, dust, and other materials swirl around at incredible speeds, heating up and emitting light and radiation. 3. How do black holes work? Gravitational pull. A black hole's immense gravity can influence nearby stars, planets, and other objects, pulling them in or affecting their orbits. Spaghettification. Anything falling into a black hole experiences extreme tidal forces, stretching objects into long, thin shapes. Hawking radiation. Theoretical physicist Stephen Hawking proposed that black holes can slowly lose mass through a process called quantum tunneling, eventually evaporating over billions of years. 4. Types of black holes. Stellar black holes, formed from collapsing stars, typically have a mass of 5 to 20 times that of the Sun. Intermediate black holes, rare and have masses between 100 and 100,000 times that of the Sun. Supermassive black holes, found at the centers of galaxies, these have masses millions or billions of times that of the Sun. Primordial black holes, hypothetical black holes formed shortly after the Big Bang. 5. Observing black holes. Black holes can't be seen directly because they don't emit light. Instead, astronomers detect their presence by observing the motion of nearby objects affected by their gravity, X-rays and other radiation from the accretion disk, gravitational waves from collisions or mergers of black holes. 6. Why are black holes important? Black holes provide insights into the nature of gravity. They are extreme testbeds for Einstein's theory of general relativity. Cosmic evolution. Supermassive black holes likely play a role in galaxy formation and evolution. The limits of physics. Studying black holes helps us explore quantum mechanics and gravity's intersection. Science fiction has often relied on the concept of black holes as a plot device, painting them as portals to other universes or as vehicles for time travel. But what happens when we take the fiction out of it? What's really going on inside those terrifying faraway entities? In short, black holes are massive pits of gravity that bend space-time because of their incredibly dense centers or singularities. When a star dies, it collapses inward rapidly. As it collapses, the star explodes into a supernova, a catastrophic expulsion of its outer material. The dying star continues to collapse until it becomes a singularity, something consisting of zero volume and infinite density. It is this seemingly impossible contradiction that causes a black hole to form. The extreme density of the new singularity pulls everything toward it, including space-time. Space-time, in a very basic sense, is the union of space and time as one four-dimensional continuum. So, what happens if you bend it? Well, if you were to experience a black hole up close, time would definitely move much differently from the way it does here on Earth. If you imagine space-time as a suspended flat plane of silly putty, then creating a singularity would be like putting a marble in the center. The marble would bend the plane downward dramatically, which would elongate any interaction with the plane toward the marble. The same thing happens with black holes, though the distortion you would experience would be a bit more severe than anything silly putty could generate. At the edge of a black hole, or the event horizon, time begins to slow astronomically. Some theories even propose that if you could survive the initial entry into a black hole, the inside would produce images of the future and the past all at once, an idea consistent with the multiverse theory of the universe. While this is an interesting concept, and no doubt the origin of many sci-fi favorites, because of the inaccessibility of black holes, there is no known way to test it. What is commonly accepted, however, is that, because of a black hole's distortion of the space-time continuum, time at the base of its event horizon passes far slower than time on Earth. Black holes are hard to find, but if you not only did find one, but also went inside it, you would discover that it is fatal. The intense gravitational force from the singularity pulls at different rates, depending on location relative to the center, which can produce a spaghettification effect on any object unfortunate enough to be caught inside. Just as the word suggests, spaghettification elongates the object in question so that it resembles spaghetti. Imagine a giant star, millions of light years away, reaching the end of its life. Over billions of years, this star burned through its nuclear fuel, shining brightly in the cosmic darkness. But now, with no fuel left to sustain the delicate balance between the outward pressure of nuclear fusion and the inward pull of gravity, the star begins to collapse. The outer layers of the star are blasted away in a supernova explosion, a brilliant display visible across galaxies. Inside the abyss picture, the black hole as a cosmic predator, hidden in the dark with no visible form. Around it, an accretion disk spins, a chaotic whirlpool of gas, dust, and shattered remains of nearby stars and planets caught in its gravitational web. The material in the disk heats up to millions of degrees, glowing in X-rays, a deadly warning to the rest of the cosmos. A spaceship approaching a black hole would experience spaghettification, stretched into thin strands, as the gravitational pull near the event horizon is exponentially stronger at one end than the other. Time for the unfortunate travelers would slow down from the perspective of distant observers, eventually freezing as they cross the event horizon. For those on board, time moves normally. The heart of the Milky Way. At the center of our galaxy, the Milky Way, lies a supermassive black hole named Sagittarius AI. This black hole, with a mass equivalent to 4 million suns, is mostly quiet, but sometimes it awakens. When a wandering star or cloud of gas strays too close, Sagittarius A feasts, creating brilliant flares of energy. Despite their destructive reputation, black holes are essential to the universe. Scientists believe that supermassive black holes, like Sagittarius A, help shape galaxies. Their immense gravity influences the motion of stars, gas, and dark matter, creating the spiral structures we marvel at in astronomical images. We may never be able to prove exactly what happens inside black holes, although many scientists are making the connection between singularities and the Big Bang Theory, which proposes that our universe exploded into existence from what could have been a singularity. Thanks for watching. Request you to subscribe the channel.